Good day. On the behalf of Joint Industry Project on Corrosion Inhibitors, I would like to welcome you all to the webinar series, Precision in Corrosion Inhibitor Selection Testing for Oil and Gas Applications. Precision is the first right step. The objectives of the webinar are twofold. One, to promote broader awareness across the industry on the need for developing standard test methods with published precision for the corrosion inhibitor evaluation and selection. The second objective of the webinar series is to understand or explain the process of developing the standard test methods. The standard test methods are not developed on their own. They require collaboration and coordination among various companies' laboratories. The third step in the webinar series is to emphasize the importance of collaboration and coordination in the development of standard test methods. And once we develop the standard test methods, they will have huge impact in our industry in terms of evaluating corrosion inhibitors. These are all the four objectives of the webinar series, especially in the discussion on the importance of collaboration. Today we have the 8th webinar. Until now, we were focusing specifically on why we need to develop standard test methods with respect to corrosion inhibitor evaluation. Starting from today's webinar, we will be focusing on the process of developing standard test methods and the importance of collaboration. Towards that, we have a good presentation from ASTM, Proficiency Test Program, Amy Baycock. I'll be introducing her later. The second broad objective of this webinar series is to promote how the Joint Industry Project on Corrosion Inhibitor is helping or moving in the direction of developing standard test methods. So for this webinar, I'll first talk about the Joint Industry Project as to where we are, and then I will let ASTM Amy Baycock to brief us about the proficiency test methods. As we all know, the major driver or the motivation for this JAP as well as the webinar series is to address the problem child. Corrosion can be controlled predominantly by four methods: good material selection, application of proper cathodic protection, application of coatings, especially to control external corrosion, and then the time-tested and proven methodology, that is application of corrosion inhibitors. We have been successfully controlling corrosion for the last 70, 80 years by either one of these methodologies or a combination of all of them. But if you look at how we are evaluating the corrosion inhibitor, the methods are still qualitative. That is a primary motivation for this JAP as well as the webinar series. Contrasting that one with other methodologies, other corrosion control strategies, such as materials, coatings, and cathodic protection, we have well-established quantitative criteria that are being used consistently across the world. So establishing quantitative criteria for corrosion inhibitor evaluation is the primary driver for this webinar series as well as the joint industry project. Again, development of these standard test methods took long time. For example, to establish the first iconic standard, that is NACE RP0169, the industry worked hard for 25 years until the first publication appeared in 1969. For coatings, extensive work was done between 1940s and 70s to establish the first 13 ASTM standards, series of standards in 1972 onwards. For materials, the famous MRO 175 or ISO 15156 was first published in 1975, but before that, the industry worked for almost 25 years. So development of standard test methods take longer time, closer to 25 to 30 years. But the development of corrosion inhibitors even took longer time because this was identified as an issue in 1993 in BAF pipeline workshop, but still we are working on it. But we believe that in another 2 years or so, we should be able to have a series of standard test methods for the evaluation of, or rather quantitative evaluation of corrosion inhibitors. I think we are in the fetal mode on that one. So that is a premises of this webinar series. Specifically, in today's webinar, webinar number 8, we are going to discuss how can corrosion inhibitor suppliers, asset owners, and third-party laboratories align on a common evaluation language. That is standard test methods with precision statement. Towards that, the ASTM Proficiency Testing Program PTP is very, very valuable. And today we are happy that we have Amy Maycock. She will be going through the ASTM PTP program. But before that, let me briefly introduce the joint industry project for those who are not familiar with this project. First of all, I would like to thank all the sponsors. We have got global sponsors of this JIP, and this sponsorship is growing. As of now, we have got 12 companies along with Core Magnet who are supporting financially this JIP. The primary objectives of the JIP are threefold. First, to collect and summarize the existing best practices from owner operators as well as chemical developers and suppliers. This objective or the phase 1 was actually completed in 2024. Between 23 and 24, we conducted 226 interviews. However, this phase 1 is still continuing. As a matter of fact, after the last webinar, we got feedback from 2 professionals that they would like to share some of their experience. So we are going to issue the second version of phase 1 as we collect more data. So as far as phase 1, the major work was done in 24, but if we have more information shared by the professionals, we will be revising that report. Phase 2 objective was to develop guidelines representing the industry best practices for the corrosion inhibitor testing based on the information we have collected in phase 1. That was also completed in 2025, and we started phase 3, which is the core of the JAP, which is to develop standard test methods for the most promising and popular methods that were identified in phase 2. Phase 3 was actually launched on December 2nd. last year. And the primary objective of phase 3 is to establish the standard test method of the 8 laboratory methodologies that were identified. To develop ASTM level standard test methods, we need to develop precision based on repeatability and reproducibility. And phase 3 will complete by publishing the repeatability statement. And then we'll talk about how we will develop reproducibility statement as required by ASTM. As I said, in phase 1, we conducted 226 interviews, and we are still looking for additional inputs on finished products, gas distribution pipelines, as well as storage tank internal. Our target was to at least get 5 different perspectives for each one of the applications. Towards that, we are looking for more inputs. However, as I said earlier, after the last webinar, we did get feedback from 2 professionals on production pipelines as well as downhole tubulars. So these numbers will go up. When you have sufficient new data, we'll be reissuing version 2 of phase 1 report. Phase 2 provided step-by-step procedure for each one of the 23 applications on how to select corrosion inhibitors, how to apply them in the field, what are the primary considerations to be considered in doing both efficiency testing as well as secondary inhibitor properties testing. We have also given, this is a core value of the phase 2 report, which is a decision-making flow chart for each one of the 23 reports. So that a person or a company can go through from step 1 all the way to inhibitor application, monitoring, and benefit from that process. In phase 2, we identified 8 methodologies that needs to be standardized. And in today's webinar, I'll be focusing little bit more on the inverted rotating disc electrode, IRDE. It is especially important to evaluate the partition coefficient, that is transfer of inhibitor from oil phase to the water phase where corrosion occurs. As explained in the previous webinars, for successful implementation of a corrosion inhibitor program, we need to cross the T's. The T's are transportability, efficiency, availability, and the secondary inhibitor properties. Among the secondary inhibitor properties, one of the key properties is the partitioning of corrosion inhibitor from the oil phase to the water phase, especially for the oil transmission pipelines. In oil transmission pipelines, we have more than 99% of oil as a carrier, and only a small percent of water is present, less than 2% by regulation. However, this water, if it settles down at the bottom of the pipeline, that is where corrosion occurs. That is where the inhibitor should act to control corrosion. The key issue here is the partitioning of the inhibitor from the oil phase into the water phase where corrosion occurs. Let us take the worst case scenario in which, for example, the inhibitor is being injected in the gas phase. That is an example of multi-phase pipeline. When an inhibitor is developed, the chemical supplier at the injection point, when they inject corrosion inhibitors, it has got 2 components. One, the active inhibitor molecule. That is a molecule that absorbs onto the surface where corrosion occurs and control internal corrosion. But to carry the active inhibitor molecule from the injection point to the location where internal corrosion occurs, the chemical suppliers also add other chemicals so that the active inhibitor molecule gets transported from different phases into the phase in which corrosion takes place. So in this example, the gray is an active inhibitor molecule. That is a molecule that has to go to the water phase, and the other chemicals are represented as red. So when you inject the inhibitor, we have got the inhibitor getting transported from the gas phase to the oil phase. As you can see, slowly the red color disappears, and ultimately the active inhibitor molecule, which is the gray, gets dissolved into the water phase, absorbed onto the surface, and control corrosion. So the inhibitor package has got two things. One, the active inhibitor molecule, that is the one that controls corrosion, and other chemicals that is required to transport the active molecule from across the different phases, and for which we commonly use the partition coefficient. We do have a standard guide, ASTM G170, that provides a guideline as to how to partition inhibitor from the oil phase into the water phase. Basically, we inject the inhibitor in the oil phase, shake it up with water phase, and drain the brain phase or water phase and conduct the corrosion testing. This is what ASTM G170 says, in which the oil phase is not present during the corrosion testing. The other way of doing it is to also have oil phase when we do the corrosion testing, for which we are contemplating of developing inverted rotating disc electrode, IRDE. The rotating disc electrode, as the name implies, is a disc that rotates, in which we can make electrochemical measurements and hence electrode. So rotating disc electrode is commonly used for more than 80 years. In fact, my PhD thesis was also on rotating disc electrode. But what we are going to do in our JAP is do the inverted rotating disc electrode. Normally, rotating disc electrode, it is placed from the top to bottom. But here, we are going to place from the bottom up so that the disc on which corrosion date can be measured is placed from the bottom, in which water accumulates. As a result, the partitioning of the inhibitor from the oil phase to the water phase can be evaluated in the presence of oil phase also. That is the premises of using the inverted rotating disc electrode that will be standardized in this JAP. So the ultimate deliverables of this JAP are: one, step-by-step procedure to carry out tests for all laboratory methodologies that will be standardized in phase 3. Distribution of blueprints of all the laboratory methodologies that will be standardized in phase 3. This will enable the sponsors to manufacture their own apparatus. To develop the standard test methods, we have to also develop or standardize solution compositions. We have identified 5 different standard solutions that need to be standardized. So in the JAP, we will establish the procedure not only to prepare the solution, but also to saturate them with appropriate gases. At the end of phase 3, we will have the precision statement based on repeatability of the laboratory methodologies that will be standardized in phase 3. In the ASTM language, precision is defined by 2 means. One is repeatability, that is the variation if the same person or the same laboratory repeats a test under the same condition multiple times. So repeatability is one person or one laboratory following the same procedure using the same apparatus. Reproducibility is multiple laboratories following the same procedure using same apparatus or similar apparatus. We envisage that at the end of the phase 3, we will have the standard test method based on repeatability. And we hope that ASTM will publish the standard test method based on the repeatability statement that would be developed in phase 3. We also anticipate that ASTM will coordinate the development of precision statement based on reproducibility, that is based on multiple laboratories. Of course, both the sponsors as well as the proponent will be actively involved in coordinating the inter-laboratories testing through ASTM. So the JIP phase 3 will complete by publishing the repeatability, and then we anticipate that ASTM will coordinate the reproducibility statement development. As per the ASTM procedure, a standard test method can be published with the repeatability statement as long as the reproducibility statement can be published within 5 years of the publication of the standard test method. So with that background, in today's webinar, we are going to hear from ASTM, Amy Makeup, on what is their proficiency testing program. And in next webinar, we'll hear from Philip on the inter-laboratory studies that will be necessary to develop the standard test method with reproducibility statement. With that background, I would like to invite Amy Makeup to give a presentation on the proficiency testing program. And Amy is the director of proficiency testing program, and she has been the director for the last 10 years. Before joining ASTM, Amy worked for a petroleum inspection and testing company. And during her time in the company, she had the opportunity to use ASTM standards as well as be a participant in many proficiency testing programs. Now ASTM is the now Amy is the ASTM side of overseeing the management and development of proficiency testing program in different industries such as plastics, metals, textile, and more. And Amy has a Bachelor of Science degree from Pennsylvania State University.